Hello everyone, welcome to lecture on wedge shaped film. I am M. Satyavani, lecturer in physics, DNR College, Bhimavaram. In this lesson, I will discuss about the wedge shaped film, how it is formed and how the interference fringes are formed using this wedge shaped film, and the next concept is derivation of fringe width, and then the determination of diameter of a thin wire using this wedge shaped film. These are all the topics I will discuss in this lesson. First of all, I will discuss about how a wedge shaped film is formed. What is a wedge shaped film? A wedge shaped film is a thin film having zero thickness at one end and progressively increasing to a particular thickness at the other end is called a wedge shaped film. In this figure, these are two glass plates. There is some thin spacer in between the two plates. In this space, a wedge shaped air film is enclosed between these two glass plates. This is about the formation of wedge shaped film. In this case, there are two glasses. One slides over on each other and they are separated by a thin spacer at the opposite edge. At this edge they are in contact, and this is a wedge shaped film. Consider two plain glass plates OA and OB inclined at an angle of theta, enclosing a wedge shaped air film. These are the two glass plates. This is the air film enclosed in between these two glass surfaces. At different points, the thickness of the air film is different. In between these two glass plates, the locus of all points having the same thickness of the air film is a straight line. When monochromatic light is incident on this combination, that is on the wedge shaped air film, it gets partly reflected from glass to air boundary. This is the glass to air boundary. Here the light is entering from glass to air. Then a part of it is reflected and a part of it is transmitted through the air. Next, again this transmitted light undergoes reflection at this glass plate, that is from air to glass boundary. These two reflected rays, these are the two reflected rays derived from the same incident ray. This is the incident ray. These two are derived from this incident ray, and this is the path followed by the first reflected ray, and this is the path followed by the second reflected ray. These two reflected rays travel over different distances and they are derived from the same ray. A single ray is divided into two reflected rays having same amplitude. Therefore, these two rays act as two rays from two coherent sources. They are in a condition to interfere and interference fringes are observed. These are straight lines parallel to the edge of the wedge. That is about the formation of interference fringes by using wedge shaped film. Next, the next concept is I want to discuss about the path difference between the two reflected rays. This theory belongs to thin films. In case of thin films, the path difference is 2 mu t cos r, and this lambda by 2 is phase change and reflection. That is, there is an extra path difference of lambda by 2 takes place when the reflection takes place backed by a denser medium. In this case, we have taken the air film. Therefore, for air film, for air refractive index is 1, therefore mu is equal to 1, and for normal incidence r is equal to 0. R is angle of refraction. When r is equal to 0, cos r is equal to 1. Substituting these values in the path difference equation, then we get, in place of 2 mu t cos r, we get 2t plus this lambda by 2. 2t plus lambda by 2 is the total path difference between the two reflected rays. Because the second ray, this is the first reflected ray, the distance travelled by the second ray is greater than the distance travelled by the first ray. Therefore, total path difference is 2t plus lambda by 2. According to the condition for bright and dark fringes, we know that if the path difference is equal to integral multiples of lambda, we get bright fringe. If the path difference is equal to in odd multiples of lambda by 2, we get dark ring. From this, we can derive that path difference 2t plus lambda by 2 is equal to n lambda, we get bright fringe, where n is equal to 1, 2, 3 and so on. Similarly, 0, if 2t plus lambda by 2 is equal to 2n plus 1 into lambda by 2, we get dark ring. If you cancel lambda by 2, we get 2t is equal to n lambda. 2t is equal to n lambda is the condition for dark ring in case of wedge shaped film. These are the conditions for bright and dark fringes formed in wedge shaped film. Next topic, we derive the formula for fringe width. We know that fringe width is nothing but it is the distance between two successive bright or dark band. For this purpose, we consider this figure. This is the wedge shaped film formed in between the two glass plates OA and OB. For example, if M and N are the number of the rings corresponding to the thicknesses Tm and Tn, then this is Tm. Here the mth fringe is formed and this is the thickness Tn. Here the nth fringe is formed. The distance between the two fringes is equal to x. This is the angle of the wedge. Theta is known as angle of the wedge. If you see the figure, this is a line and this is another line. These two are parallel lines. OB is a transversal. When these two are parallel lines, this is a transversal. This angle is equal to this angle. In case of a parallel lines, we know that when a transversal cuts the two parallel lines, alternate angles are equal, etc. in our mathematics. Therefore, this angle is also equal to theta. These two are equal. If Tm and Tn corresponds to the thickness of air film for mth and nth dark fringes, then 2Tm, according to theory of dark fringe, 2t is equal to n lambda, 2Tm is equal to m lambda. Tm is the thickness corresponds to the mth fringe and Tn is the thickness of the air film corresponds to nth fringe. Subtracting these two equations, we get 2 into Tn minus Tm is equal to n minus m into lambda. Tn minus Tm is equal to n minus m into lambda by 2. From the figure, if you take this triangle, tan theta is equal to, this is Tm and this length is Tn, then this small part becomes equal to Tn minus Tm. This is Tm and this is equal to Tn, then this part is equal to Tn minus Tm. From this small triangle, tan theta is equal to, we know that tan theta is equal to opposite side by adjacent side. Opposite side is Tn minus Tm and adjacent side is x. Then tan theta is equal to Tn minus Tm by x, where x is the distance between mth and nth dark fringes. As in between the two glass plates, generally we place a narrow wire or thin air, etc. Therefore, the thickness of the film is very thin. Thin film means it has thickness in the order of angstroms. Therefore, the angle of the wedge is very small. But in calculation purposes, we see the figure just like this. But these two glass plates are very close to each other because the spacer between the two glass plates is very thin copper wires in electrical wires and thick hair. Therefore, its thickness is very small. Therefore, angle of the wedge is also very small. In calculus, we know that when angles are very small, sin theta is equal to theta and tan theta is also equal to theta. Then this equation becomes theta is equal to Tn minus Tm by x, or Tn minus Tm is equal to x into theta. If you observe these equations 3 and 4, the left hand side we have Tn minus 2m. Therefore, as left hand sides are equal, right hand sides are also equal. From 3 and 4, we get x theta is equal to n minus m into lambda by 2, or x by n minus m is equal to lambda by 2 theta. This is the distance between mth to nth ring, and x by n minus m indicates distance moved by number of fringes. This is nothing but fringe width. This fringe width is denoted by beta. Therefore, in place of x by n minus m, we can write beta. Beta is equal to lambda by 2 theta, where lambda is the wavelength of monochromatic light used and theta is the angle of the wedge. If lambda is known, theta can be calculated by measuring beta. Next, if there is a film of refractive index mu, generally we conduct experiments in laboratory, then the thin film is air film, then refractive index mu is equal to 1, then beta is equal to lambda by 2 theta. For example, in place of air, if you place an oil, etc., or any transparent substance like mica, etc., then its refractive index is mu, then this formula becomes beta is equal to lambda by 2 mu theta. This is the expression for fringe width. If you observe this equation, beta depends upon lambda, angle of the wedge, and refractive index. In general, in laboratories, air is taken, then mu is equal to 1. In general, beta depends upon lambda and theta. But there is no n in this expression. That means beta is independent of n, and it does not depend upon the number of the fringe. So all fringes are equally spaced. From this equation we can say that it does not depend upon, if it depends upon n, different fringes, different places have different fringe widths, but beta does not depend upon n, it is independent of n. So all fringes are equally spaced. That is about interference fringes formed by wedge film and expression for fringe width in case of wedge film. Next, this wedge film arrangement is used to determine the diameter of thin wires. For the measurement of diameters of cylinders, thick wires, etc., we use generally, for cylinders, etc., we use vernier calipers. For very small wires, we use screw gauge. But when the diameters are less than the 100th part of the centimeter, then we use this method for the determination of diameter. Generally, this method is used for wires of very small diameter. They are in the diameter is in the order of angstroms. For this purpose, generally we use A thin wire in electrical wires, copper wire in electrical wire, or generally a thick hair is used as the wire. Using this experiment, the diameters of very thin wires is calculated very accurately. So, diameter of the wire is determined by this experiment. For the determination of diameter of the wire, the experimental setup is as shown in the figure, and the wire whose diameter is to be determined is placed in between the two glass plates. Then a thin film of wedge shaped air film is formed between these two glass plates. This is the experimental setup. S is a monochromatic source of light of wavelength lambda. Generally, sodium lamp is used in this case, and sodium light is taken as monochromatic light. Monochromatic light is necessary for the production of formation of interference fringes. Therefore, generally sodium light is used in this case, and the light from this monochromatic source, sodium light, is allowed to incident on a convex lens. When this is at the focus of the lens, when the light from S is incident on the convex lens, they become parallel after refraction. These parallel rays are allowed to incident on a plain glass plate G, which is making an angle 45 degrees with the incident rays, path of the beam. This is the path of the beam coming from the lens, and these rays are making an angle 45 degrees with the glass plate. The light, we know that in the laws of reflection, when the angle of incidence is 45 degrees, then the rays reflect theta, then the rays reflected by 2 theta. Then the reflected ray becomes normal as theta. Here the angle made by the parallel rays with the glass plate is 45 degrees, then it is reflected through 90 degrees, and that means the rays are normal. These rays are normal rays are allowed to incident on this combination. The normal rays are allowed only, normal rays only are allowed to incident on this combination, because in the theory we have substituted R is equal to 0. It is possible only when the incidence is normal incidence. For this purpose, the rays are allowed to incident normally on the combination. Normally, then the reflected rays from the lower and upper portions of the thin film interfere with each other, and interference fringes are observed through the eyepiece. Next, measurement of fringe width. First of all, the vertical crosswire is made to coincide with one of the bright fringes, say mth fringe, and the reading is noted. Next, the microscope is moved until the crosswire coincides with the nth bright fringe. Again, the reading is noted. The difference of these two readings is equal to distance moved by the microscope, which is equal to x. We know that fringe width is equal to distance moved by the screw by number of fringes. We are moving from mth fringe to nth fringe, therefore number of fringes when the crosswire crosses is equal to n minus m. Distance moved by the screw is equal to x, then fringe width is equal to x by n minus m. Next, from the figure, these are the two glass plates. This is the angle of the wedge, and this is the cross section of the wire placed. This is the diameter. This is the diameter of the wire. and L is the distance between the point of contact of two glass plates and the wire, distance between the axis of the wire and the point of contact of two glass plates. From this figure, this is a triangle. Tan theta is equal to opposite side by adjacent side, that is equal to d by L. R theta is equal to d by L, as angle of the wedge is very small. We know that fringe width beta is equal to lambda by 2 mu beta. In last slide we have derived the formula for fringe width. Beta is equal to lambda by 2 theta. Beta is equal to lambda by 2 mu theta, or theta is equal to lambda by 2 mu beta. These are the two equations for angle of the wedge. We have to determine the value of d, diameter of the wire. For this purpose we remove the another unknown quantity, angle of wedge. Then from these two equations, left hand sides are equal, that is theta, then right hand sides are automatically equal. Lambda by 2 mu beta is equal to d by L, or d is equal to lambda L by 2 mu beta. We can calculate L and beta using microscope. We can calculate beta, and we have already know the value of wavelength of monochromatic light. Then substituting the values of lambda, L, mu and beta, we get the diameter of the wire. This is about the determination of diameter of the wire by wedge shaped film. That is about wedge shaped film. Once again I conclude this lesson. Wedge shaped film is one whose thickness varies from one end to another, as shown in the figure. It is formed by placing a thin spacer at one end, then a thin wedge shaped film is formed. In case of wedge shaped film, a single ray of light is divided into two rays having equal amplitudes, and these two reflected rays appear to come from two coherent sources, and interference fringes are observed. That means the amplitude of a single ray is divided into two rays having equal amplitude. Therefore, this belongs to type of interference by division of amplitude. In this case, a thin film is formed, and the rays reflected from the thin film interfere with each other, and alternate bright and dark lines, straight lines, parallel lines are observed. These are known as interference fringes, or fringes of equal thickness. Next, we have derived about the fringe width. Fringe width is nothing but distance between any two successive or consecutive bright or dark fringes. The formula for beta is lambda by 2 mu beta. That means beta depends upon wavelength of light used and the angle of the wedge. The final one is determination of diameter of a thin wire. In case of very thin wires, screw gauge or vernier caliper screw gauge are not suitable. For high accuracy, this method is used. First of all, a wedge film is formed by placing the small wire in between two glass plates whose diameter is to be determined, and then we observe interference fringes through the eyepiece. Then by taking the readings, by coinciding the vertical crosswire with mth and mth rings, we can calculate beta, and substituting the values of beta, wavelength of light lambda, and distance between the point of contact and the wire, by substituting the all values in the equation, we can calculate diameters of thin wires. This wedge method is also useful for testing the flatness of the glass plates also. When the glass plate is not flat, that means not thickness is not uniform, then the fringes of equal thickness are not observed. By using that phenomena, we can also test the flatness of the surfaces of the glass plates. These are all the uses of wedge shaped film.